History.
All right, let's take a look at a vertical oscillator. We've been looking at horizontal oscillators, and the nice thing about horizontal oscillator is that there's only one force acting on it. One unbalanced force. All we have on this thing is we have the normal force up and the weight down, and then we have the spring either applying a force this way or the other way. So this is the only unbalanced force, the spring. So that's nice and simple. A vertical oscillator seems more complicated. Because if we look at this, we have the weight and we have the spring, and at various times the spring is greater than or less than the weight, and so this is a little more complicated, especially when if we start looking at energy, because we would have spring potential energy, gravitational potential energy, and kinetic energy. So and it would get it seems like it'd get significantly more complicated. But it turns out, from an analysis standpoint, all we need to really think about as far as gravity is that gravity just establishes our equilibrium position. Right? So when we have this here, that is our new equilibrium position. And then it behaves as if there is only one force on it, and that is the spring force. F equals K delta Y in this case. But this would be right here. Our, there's our new equilibrium position, something like that. So then it'll oscillate back and forth. And we're just going to analyze this like a horizontal oscillator, even though it's moving vertically. And gravity's the only thing we're going to worry about with gravity is it's going to establish where this new equilibrium position is. So we're going to continue to use this model. And when we use our energy model, the total energy is going to be 1/2 Ka squared, or 1/2 mv max squared, or 1/2 kx squared plus 1/2 mv squared. Right. So we're going to use the same thing. We're not going to use gravitational potential energy. We're only going to look at the spring potential energy. We're going to treat it as if it's a horizontal oscillator. All right. So with that in mind, I have a spring, and here it is before I've attached a weight to it. And now we've added a 50-gram weight to it. What I want you to do is find the spring constant of this 50-gram weight on this spring, and I want you to do it two ways. One, do it with the measurements. I just showed you a bunch of measurements, so you should be able to figure out what the spring constant is with measurements. And next, using time. I have time code burned in here, so you can measure the period and figure out from the oscillation what is the spring constant. All right, why don't you take a moment to do that?
Pause the video now.
All right, let's try an AP problem. This is from 1989, and the block falls and sticks to that plate of negligible mass. Determine the speed of the block, the distance the instant it hits the end of the spring. All right, so that's just a conservation of energy problem. So what do we have? We have, for this, I'm going to say that the gravitational potential energy is 0 here. And so that's 0, and that's 1. Energy at 0 equals the energy at 1. So we have gravitational potential energy is 0 equals the kinetic energy at 1. So mgh0 equals 1/2 mv1 squared. Masses go away. v1 equals the square root of 2gh0. 2 times, and if I use 10 newtons per kilogram for g, 0.45 meters. So we end up with 3 meters per second. All right, just using conservation of energy. That was part A in the 1989 exam. All right, so V1. All right, determine the period of the simple harmonic motion that ensues. All right, so this is a vertical oscillator, and we know it works like a horizontal oscillator. Omega equals the square root of k over m. You could derive that using conservation of energy, and I would encourage you to do that. I'm not going to do that right now. And this equals, what the period, this is 2 pi over p over the period. So therefore the period equals 2 pi square root of m over k, 2 pi square root of 2 kilograms times 200 newtons per meter. Right. And it gives us 0.628 seconds, something like that. All right. Our oscillator behaves just like a horizontal one, right? So omega is the same as we had been doing. Determine the distance the spring is compressed at the instant the speed of the block is maximum. Well, you have to understand that the speed of the block is maximum when it's in its equilibrium position, because it's falling, it's accelerating down because the force of gravity is the only force acting on it here. And then when it presses on the spring, the force of gravity is going to be greater than the spring pushing up for a certain distance until it gets to the equilibrium position, wherever that is. It gets to that equilibrium position, and at that point, it's at its maximum speed, and it's going to start slowing down, because if the equilibrium position was here, when you're below here, the spring is starting to push up greater than the weight down, and so it's slowing down at that point. So really, determine the distance the spring is compressed. So really, we need to figure out if we gently set this on here, how much would it compress? And we're going to use Hooke's law to do that. Force of the spring is minus k delta y. Right? We want to know delta y. That's the compression. So delta y equals the force of the spring divided by k. And that is going to be, force of the spring is actually, at the equilibrium position, is going to be the weight, mg over k, equals 2 kilograms. I'm going to use 10 newtons per kilogram. And k is 200 newtons per meter. All right, so I guess that's 0.1 meter. 0.1 meter for C. All right, so that is that's the distance the spring is compressed when it gets to its maximum speed. You need to realize the maximum speed is attained at the equilibrium position. Before that, it was speeding up. After that, it will be slowing down. And then the next question, determine the maximum compression of the spring. All right. So so this is going to, let me get rid of this. This thing's going to hit, it's going to oscillate, and it's going to have some maximum compression. This is the equilibrium position. It's going to get down to here. This would be negative A, and it's going to oscillate between wherever negative A and positive A is, actually I probably have to go lower than this just by looking at the symmetry. Negative A is going to be down here somewhere. A is going to be up here somewhere. It's going to oscillate between these two places. I know that A has to be above this because when it was here, it had kinetic energy. So when it gets back up to here, it's going to continue to have kinetic energy. So it's going to be trying to go higher, but it's stuck to the plate because they said it's going to stick. So it's going to oscillate a little higher, then come down, and it's going to oscillate about that center point. So we need to figure out what the amplitude of this oscillation is. And it says determine the maximum compression of the spring. And the maximum compression is going to be A plus whatever this compression was. And then later they asked determine the amplitude of the simple harmonic motion. If I had this amplitude, since I already know what this is 0.1 meter, right? This compresses 0.1 meter here. And so I think I'm going to find A. All right, I'm going to use conservation of energy to find A. I know that the energy when this is oscillating isn't going to change. So I'm going to say that 1/2 Ka squared, all right, I want to know A, equals 1/2 mv squared plus 1/2 kx squared. All right, well, we want to know that. We know K, we know the mass, and we know, because we already figured it out, the speed at this point, right? This thing's going to be oscillating back and forth, and there's this intermediate point where we know, not only do we know what x is, because we calculated it, x is the compression was 0.1 meter, right? That's x at that point, and we know the speed, right? So we know the speed, we know the mass, we know x. Okay, so we can solve that for A. So we're going to use that to solve for A. Once we have A, we can figure out what the total compression was, total max compression. All right, so let's solve this for A. Get rid of our 1/2s. And I got A equals the square root of, what do we got, mv squared plus kx squared all over k. We have mass is 2 kilograms. V at that position is 3 meters per second squared plus K, 200 newtons per meter. 0.1 meter. 0.1 meter squared divided by K, which is 200 newtons per meter. So that looks like we end up with like 0.316 meters. That is A. That is A. That's the distance between here and here is A. And that was the answer to question E. And then we just need to go back to get D. D said the maximum compression of the spring. Well, it's going to be A plus this compression, the distance from when nothing was on it to when it got to its equilibrium position, which is 0.1 meter. So D, the answer to D is max compression. Max compression equals 0.36 meters plus 0.1 meter is 0.416 meters. All right. So there's our maximum compression. All right, so we just treated this really like a horizontal oscillator. The initial part, obviously it fell and we weren't dealing with simple harmonic motion. But once it started oscillating, we were just, when our conservation of energy, we don't take into account that the gravitational potential energy is changing. It is. But we're ignoring that and we're treating this is gravity's only function is to establish a new equilibrium position. And there you go. All right, so to find the spring constant, two ways. You can use Hooke's law. F equals K delta Y in this case. So you have the measurement to get delta Y. So K equals the force on the spring delta Y. In this case, the force on the spring is the weight, which is mg over delta Y is K. All right, so you can plug the numbers in to get that. I don't have the numbers handy, but you can do that. And then the other way to do it was with the oscillation, right? So this behaves just like a horizontal oscillator, where omega equals the square root of K over M. Know how to derive that with using conservation of energy. I did that in a previous video. Make sure you can do that. But you know, I can really measuring the period is what I want to do, and so that's going to be 2 pi over t, because I can measure the period quite easily, especially got that burned in time code. K equals 4 pi squared m over t squared. So measure t squared. The mass was what was that mass? 50 grams. 4 pi squared. 0.05 kilograms divided by whatever t squared is. Should give you K, and those should be pretty close to the same thing. I don't have the numbers handy because I don't have access to the video right now. I didn't measure it, but you do, so you should be able to confirm that. Make sure those numbers are pretty darn close. All right, so a horizontal oscillator behaves, a vertical oscillator behaves just like a horizontal one. The only thing that gravity does is establish where this equilibrium position is, right? Where is that? So now we can model it just like this. Oops. Right? And that makes our lives a lot easier than trying to include gravity, especially with energy, where we would have to include gravitational potential energy along with spring potential energy, and that would be a pain in the neck. So we don't want to do that. So there you go. Horizontal oscillator.
Extreme physics.